When you think of Saturn, you probably picture a peaceful golden world floating in the dark, wrapped in those glowing rings, elegant, still, almost dreamlike. But what if I told you that Saturn is the most terrifying planet in our entire solar system, and that hidden beneath its golden surface is a reality so violent, so alien, and so deeply strange that some of what we have found there still cannot be explained by our best science? This is not the Saturn you learned about in school. This is the Saturn that kept scientists awake at night, and something about this planet does not make sense. Let us start with what you can see from a distance. Saturn looks calm. From Earth, through even a basic telescope, it appears as a pale gold dot with a thin, bright line around. Those are the rings. And for centuries, that is all we knew. A quiet world far away with a beautiful accessory. Tonight's journey is brought to you by Beyond the Stars, a full collection of overnight cosmic sleep journeys available at mycosmicdrift.com. Link in the description. But appearances can be deeply misleading because Saturn is not calm, not even close. The wind on Saturn never stops. It screams across the upper atmosphere at speeds that would make anything on Earth seem like a gentle breeze. We are talking about sustained winds of over 1,100 miles per hour near the equator. To put that in perspective, the strongest tornado ever recorded on Earth topped out at around 300 miles per hour. And that was a brief, chaotic event that lasted minutes. On Saturn, those winds are permanent. They are not storms. They are the weather. Every single day, every single hour, for billions of years, the air on Saturn does not rest. It cannot. The forces driving those winds are so powerful and so constant that they have shaped the entire atmosphere into thick horizontal bands of swirling gas, each one moving at a different speed, each one grinding against the next like layers of a machine that was never designed to stop. And here is what makes it worse. You cannot stand on Saturn. There is no ground. Saturn is a gas giant. It is made almost entirely of hydrogen and helium. If you were somehow dropped into its atmosphere, you would not land. You would fall. First through cold, thin clouds of ammonia ice, then through thicker, darker layers. The temperature would rise. The pressure would build. And as you sank deeper, the gas around you would become denser and denser until it stopped behaving like a gas entirely. It would begin to feel like a liquid, a thick, crushing ocean of hydrogen, squeezed so hard by gravity that it started conducting electricity. This is called liquid metallic hydrogen, and it is one of the strangest substances in the known universe. On Earth, hydrogen is the lightest element, a gas so thin you cannot see it or feel it. But inside Saturn, under pressures that exceed 1,000,000 times the pressure of our atmosphere at sea level, hydrogen transforms. Its atoms are squeezed so tightly together that their electrons break free and begin to flow between them. Just like electrons flow through a copper wire, it becomes a metal, not a solid metal like iron or gold. A liquid metal, a hot, thick, electrically conductive fluid that fills the interior of the planet like a vast underground sea, thousands of miles deep. This liquid metallic hydrogen is what generates Saturn's magnetic field, a magnetic field that extends millions of miles into space and wraps around the planet like an invisible shell. And deep beneath that metallic ocean, at the very core of Saturn, the conditions are almost unimaginable. Temperatures reach nearly 21,000 degrees Fahrenheit. That is hotter than the surface of the sun. The pressure is so intense that it could crush anything we have ever built. Rock, steel, diamond, it does not matter. At those depths, matter behaves in ways we are still trying to understand. Scientists believe there is a dense core of rock and ice down there, roughly 15 to 18 times the mass of Earth. But no probe has ever reached it. No instrument has ever measured it directly. We are guessing, based on how the planet pulls on nearby objects and on the way it wobbles as it spins. The core of Saturn is one of the most extreme environments in our solar system, and we know almost nothing about it. Now, let us talk about what is above that core, because the surface, or rather the visible cloud layer, is where Saturn becomes truly unsettling. You have probably seen pictures of Saturn's famous hexagon. It is a six-sided storm sitting directly over the North Pole of the planet. Each side of this hexagon is longer than the diameter of Earth. The entire structure stretches about 20,000 miles across, and the winds within it howl at over 300 miles per hour. It has been there since at least 1981, when the Voyager 1 spacecraft first photographed it. That was over 40 years ago. And when the Cassini spacecraft arrived at Saturn in 2004, the hexagon was still there. Same shape, same size, same location. It had not moved. It had not faded. It had not changed its form in any meaningful way. Think about that for a moment. On Earth, a hurricane might last a week or two before it falls apart. Even the most persistent weather systems eventually dissipate. But this hexagonal storm on Saturn has been raging for at least 4 decades. And some scientists believe it has been there for centuries, maybe longer. And here is the part that still puzzles researchers. It is a hexagon, not a circle, not an oval. A six-sided geometric shape, perfectly defined, sitting at the top of a chaotic, turbulent atmosphere. Storms are not supposed to look like that. Weather does not organize itself into straight lines and sharp angles. Weather is messy, random, unpredictable. And yet, there it is. A hexagonal jet stream with edges so clean and so stable that when scientists first saw it, some of them refused to believe it was real. They thought it might be an artifact of the imaging process, a glitch in the data, but it was not. The hexagon is as real as anything else on Saturn, and it should not exist. Researchers have spent years trying to figure out what causes it. In laboratory experiments, scientists have tried spinning fluids at different speeds to see if they could recreate similar shapes. And they could. By rotating a liquid at one speed in the center and a different speed at the edges, polygonal patterns emerged. Triangles, squares, pentagons, hexagons, even octagons. The key was the difference in rotation speed between the inner and outer layers of fluid. When the speed differential hit a certain sweet spot, six-sided shapes formed. This gave scientists a possible explanation. Saturn's north polar jet stream might be moving at just the right speed relative to the surrounding atmosphere to produce a standing wave pattern in the shape of a hexagon. But there is a problem with this explanation. It works in the lab. It does not fully work on Saturn. Because lab experiments create these shapes in controlled environments with rigid boundaries. Saturn has no rigid boundaries. Its atmosphere is a churning, dynamic, unpredictable mess of gas and wind. There is nothing holding this hexagon in place. No wall, no barrier, no physical structure to anchor it. And yet it stays, decade after decade, perfectly stable, perfectly shaped, rotating with the planet as if it were bolted onto the atmosphere itself. A team at Harvard proposed in 2020 that the hexagon might actually extend thousands of miles deep into Saturn's interior, rooted in powerful convection currents far below the visible cloud layer. Their computer simulations showed that turbulent compressible convection the violent churning of compressed gas deep inside the planet, could generate vortexes that pinch the polar jet stream into a polygonal shape. Think of it like squeezing a rubber band from the outside with several smaller rubber bands. The central ring gets compressed into a shape with edges. The more pressure points you have, the more sides the polygon gets. On Saturn, the number of surrounding vortexes happens to favor a six-sided figure, but even this model is not perfect. Their simulations actually produced a nine-sided polygon, not a hexagon. Close, but not exact. And there are still features of the real hexagon that no model has fully reproduced. For instance, the hexagon changed color between 2012 and 2016. During the long Saturnian winter, when the North Pole was shrouded in darkness, the hexagon appeared blue. But as spring arrived and sunlight returned to the northern hemisphere, it shifted to a golden hue. Scientists think this might be because sunlight triggered chemical reactions in the upper atmosphere, creating a haze that changed the color, but they are not entirely sure. The hexagon keeps its secrets well, and at the center of the hexagon sits something even more dramatic: a massive vortex, a hurricane-like storm with an eye about 50 times larger than a typical Earth hurricane. The winds at the wall of this vortex reach speeds double that of the strongest cyclones on our planet. But unlike hurricanes on Earth, which feed on warm ocean water, this storm has no ocean beneath it. There is no water driving it. There is no surface at all. It is a hurricane with no fuel source that we can identify, spinning endlessly at the top of a planet made of gas, inside a hexagonal cage that defies the laws of atmospheric physics. Saturn's south pole also has a vortex, a large, violent, hurricane-like storm with a distinct eye, roughly 8,000 kilometers across. But there is no hexagon in the south, just the vortex. Why the difference? Why does one pole have a perfectly geometric jet stream and the other does not? Nobody knows for certain. Some researchers point to differences in seasonal heating. Others suggest it has to do with variations in the deep atmospheric structure. But the truth is, we do not have a complete answer. The asymmetry between Saturn's poles is another puzzle that remains open. Let us shift our attention now, away from the storms, toward the rings. Saturn's rings are the most famous feature in our solar system. They stretch out nearly 200,000 miles from the planet. If you could drive a car at highway speed across them, it would take you over 100 days. And yet, despite their enormous width, the rings are astonishingly thin. In most places, they are only about 30 feet thick. That is roughly the height of a 3-story building. Imagine a sheet of paper stretched across the length of a football field. That gives you a sense of the proportions. The rings are flat. Almost. Impossibly flat. A razor-thin disk of ice and rock and dust, orbiting a giant planet in near-perfect alignment. The rings are made of billions of individual particles. Some are as small as grains of sand. Others are as large as houses. A few are as big as mountains. Most of them are water ice. Pure, bright, reflective water ice, with just a tiny amount of rocky material mixed in. They orbit Saturn at different speeds, depending on their distance from the planet, just like planets orbit the Sun. The inner particles move faster. The outer particles move slower. And all of them are locked in a delicate gravitational dance, bumping into each other, clumping together, breaking apart, endlessly recycling. For a long time, scientists assumed the rings were as old as Saturn itself, born together during the formation of the solar system about 4.5 billion years ago. But recent evidence has shattered that assumption, and the new picture is far more disturbing. During its final years, the Cassini spacecraft performed a series of daring dives between Saturn and its innermost ring. These grand finale orbits, as they were called, brought Cassini closer to the planet than any spacecraft had ever been. And during those passes, the spacecraft measured something critical: the mass of the rings. By tracking how Cassini was pulled by the gravity of both Saturn and its rings, scientists could separate the two forces and weigh the rings directly. The result was a surprise. The rings were lighter than expected, much lighter. Their total mass came out to roughly 40% of the mass of Saturn's small moon Mimas. That might sound like a lot, but Mimas itself is tiny. It is only about 250 miles across. For a ring system that stretches across hundreds of thousands of miles, that is not much material at all. And here is why that matters. The mass of the rings tells us how long they have been exposed to the constant bombardment of interplanetary dust. Tiny particles from asteroids and comets are always raining down on the rings from outer space. Over time, this cosmic dust should darken the ice, like soot collecting on a white carpet. The longer the rings have been there, the dirtier they should be. But the rings are remarkably clean, bright, reflective, almost pure water ice. That means they have not been sitting there for billions of years. They are young, shockingly young. The best estimates now suggest that Saturn's rings formed somewhere between 10 million and 400 million years ago. In cosmic terms, that is practically yesterday. When the rings were born, dinosaurs may have still been walking the Earth, or they may have already gone extinct. Either way, Saturn spent most of its existence as a ringless world. The planet we see today, with its iconic halo of ice, is a relatively recent version of itself. And the rings are not going to last. They are disappearing. Right now. Material from the inner rings is constantly falling into Saturn's atmosphere in a process called ring rain. Every second, tons of ice particles spiral inward along the planet's magnetic field lines and plunge into the atmosphere. At the current rate, some estimates suggest the rings could be completely gone within the next 100 million years. Maybe sooner. The most beautiful feature in our solar system is temporary. It is fading as you listen to these words. So what created the rings? If they are not primordial leftovers from the birth of the solar system, then something must have happened. Something violent. Some kind of catastrophe. The leading theories suggest that a comet or asteroid wandered too close to Saturn and was torn apart by the planet's immense gravity, its icy remains spreading out into a disk. Another possibility is that one of Saturn's moons was destroyed, either by a collision with another object or by tidal forces that ripped it apart when its orbit decayed too close to the planet. Either way, the rings are the debris of a disaster. A frozen crime scene spread across hundreds of thousands of miles, slowly dissolving into the planet that created it. There is an invisible line around Saturn called the Roche limit. It is the distance within which the planet's tidal forces become stronger than the internal gravity holding a body together. Cross that line, and you will be pulled apart, stretched, shattered, reduced to rubble. Saturn's main rings exist within this zone. That is why they are rings and not moons. Any object large enough to hold itself together that drifts inside the Roche limit will be torn to pieces by the planet's gravity. The rings are a graveyard of objects that got too close. But there is something even stranger happening in the rings, something that scientists first noticed in the early 1980s and still cannot fully explain. They are called spokes. Spokes are ghostly radial markings that appear in Saturn's B ring, the brightest and densest of the main rings. They look like dark or bright streaks radiating outward from the planet, like the spokes on a bicycle wheel. Some of them stretch over 10,000 miles long, that is wider than the diameter of Earth, and they appear and disappear on timescales of hours. One moment the ring looks normal. The next, these enormous features have materialized out of nowhere. And then, just as suddenly, they are gone. The Voyager spacecraft first spotted them in the early 1980s. Scientists were fascinated and baffled. Spokes should not exist. The particles in Saturn's rings orbit the planet according to standard gravitational mechanics. Inner particles move faster. Outer particles move slower. Any radial feature, anything that lines up from the planet outward, should be sheared apart almost immediately by this difference in orbital speed. It would be like drawing a straight line across a spinning record. The line would warp and twist within seconds, and yet the spokes persist for hours before they fade. The leading theory is that spokes are made of tiny ice particles, smaller than the width of a human hair, that are lifted above the ring plane by electrostatic forces. Think of it like the way static electricity can make your hair stand up. Something charges these microscopic grains, repelling them from the larger ring particles below and suspending them in a thin cloud above the ring surface. When sunlight hits these suspended particles at certain angles, they show up as bright streaks. At other angles, they appear dark against the brighter background of the ring. But what charges them? That is the real mystery. One idea is that meteoroid impacts kick up dust and generate localized electric fields. Another is that lightning in Saturn's atmosphere, which is thousands of times more powerful than lightning on Earth, sends electromagnetic pulses through the magnetic field that interact with the ring particles. A third possibility is that instabilities in Saturn's own magnetic field create fluctuating electric fields near the ring plane. The truth is, no single theory has been able to explain everything we observe about the spokes: their timing, their location, their shape, their seasonal pattern. Because spokes are seasonal, they come and go with Saturn's year. During the Saturnian midsummer and midwinter, they vanish. As Saturn approaches its equinox, the point in its orbit where the sun shines directly on the ring's edge-on, the spokes return. Between 1998 and 2005, no one saw any spokes at all. Then, as Saturn's seasons shifted, they reappeared. Cassini captured them returning in 2005, earlier than expected, and tracked their activity for years. Their frequency increased dramatically when the sun was within about 10 degrees of the ring plane. Some scientists believe this seasonal pattern is tied to changes in Saturn's magnetosphere. Others think it is related to the way ultraviolet light from the sun interacts with the ring particles at different angles. The investigation continues. Now let me take you somewhere even more disturbing, deep into the atmosphere, into the storms. Saturn looks bland compared to Jupiter. Where Jupiter has vivid swirls and the famous Great Red Spot, Saturn appears smooth and hazy. Its bands of cloud are wider and fainter. Its colors are muted, gold, tan, cream. It looks, from a distance, like a peaceful world, but this calm surface is an illusion. Saturn stores its fury. It builds pressure. It waits. And then, roughly once every 30 Earth years, it erupts. These eruptions are called great white spots. They are planet-encircling megastorms, so large and so bright that you can see them from Earth through a telescope. The first one was recorded in 1876 by the astronomer Asaph Hall. Since then, 5 more have been observed, the most recent in December 2010. That storm was observed in spectacular detail by the Cassini spacecraft, and what it revealed was staggering. The 2010 Great White Spot began as a small bright cloud in Saturn's northern hemisphere, about 800 miles across. Within 3 weeks, it had grown to over 10,000 miles from north to south and 17,000 miles from east to west. Its tail stretched 1/3 of the way around the planet, a distance of over 62,000 miles. Within 12 weeks, the storm clouds had wrapped entirely around Saturn. If you could have laid this storm flat on Earth, it would have blanketed most of North America from coast to coast and circled the globe. The storm head rose about 40 to 50 kilometers above the surrounding cloud deck, punching upward with such force that it delivered fresh water ice from deep inside the atmosphere, over 200 kilometers below. The cloud tops were highly reflective, coated in this fresh ice, and they were lit with constant lightning. Not the kind of lightning you see in a summer thunderstorm. Saturn's lightning is different. Its discharges are thousands of times more powerful than anything on Earth, capable of outshining the sun for a fraction of a second in radio wavelengths. During the 2010 storm, Cassini detected 10 of these Saturn electrostatic discharges per second, each one a titanic explosion of energy deep within the storm. But the weirdest part came after the visible storm died. The head of the storm faded after about 7 months. The clouds dissipated. The lightning stopped. But in the stratosphere, high above where the storm had raged, something unprecedented was happening. 2 warm air masses, heated by the storm, had formed and were drifting toward each other. When they merged, the temperature in that region spiked by 150 degrees Fahrenheit above normal. A massive vortex formed, and then the atmosphere released an enormous cloud of ethylene, a gas that has no known natural source in those quantities on Saturn. Scientists were shocked. Nothing in their models predicted this. The storm had literally burped something into the upper atmosphere that should not have been there. And then, silence. For another 3 decades, give or take, Saturn will look peaceful again. The atmosphere will settle, the bands will smooth out, and the planet will quietly build toward its next eruption. Why does this happen? Why do these megastorms occur only once every 30 years? The answer lies in something deceptively simple. Water. On Saturn, water molecules are heavier than the hydrogen and helium that dominate the atmosphere. So the water sinks. It separates out and forms a wet layer deep below the visible clouds. This wet layer acts as a cap, suppressing convection. Warm air cannot rise the way it normally would. The atmosphere becomes stable, too stable. Energy accumulates, heat builds, and over the course of decades, the upper atmosphere slowly cools. Eventually, it cools so much that it becomes dense enough to sink on its own, displacing the warm, moist air below. That moist air rockets upward, carrying enormous quantities of water vapor to the cloud tops, and the result is a catastrophic explosion of convective energy. A planetary thunderstorm that makes every hurricane on Earth look like a passing shower. Scientists at Caltech confirmed this mechanism in 2015, using models that match the Cassini observations of the 2010 storm. They also suggested that the reason Jupiter does not produce similar planet-encircling storms might be because Jupiter's atmosphere contains less water. Without that heavy wet layer to suppress convection, Jupiter releases energy more continuously, preventing the kind of buildup that Saturn experiences. Saturn stores its rage. Jupiter lets it out gradually. 2 giant planets, 2 completely different tempers. Now let me play you something. Or, rather, let me describe it to you. Because in 2002, while the Cassini spacecraft was still 374 million miles from Saturn, its instruments picked up something haunting. Radio emissions, not visible light, not heat. Radio waves, generated by the interaction between Saturn's magnetic field and its auroras, the glowing lights that dance near the poles, similar to Earth's northern and southern lights, but on a scale that dwarfs anything we experience. When scientists at the University of Iowa converted these radio waves into audio, shifting the frequency down into the range of human hearing, the result was unlike anything they had heard from another planet. It sounded eerie, unsettling, like a haunted soundtrack. Rising and falling tones, sweeping through frequencies in patterns that were complex and almost musical, but in a way that felt deeply alien. The researchers described it as something that could be mistaken for a Halloween soundtrack. The signals came in waves, pulsing with changes in frequency and intensity, mapping out the invisible dynamics of Saturn's magnetic environment. Scientists noticed that the structures in these radio emissions were remarkably similar to the auroral radio emissions produced by Earth, but on a much grander scale. And then, during Cassini's final weeks in 2017, as the spacecraft made its last desperate orbits before plunging into Saturn's atmosphere, it captured something else. A powerful electromagnetic interaction between Saturn and its moon Enceladus. Plasma waves traveling in a circuit between the planet and the tiny icy moon, riding along the magnetic field lines like electricity through a wire. When this signal was converted to audio, it sounded like a high-pitched whisper of wind, a conversation between a giant and a speck, an exchange of energy across hundreds of thousands of miles of empty space, inaudible to any ear, detectable only by instruments designed to listen to the voices of planets. These sounds are not sounds in the way we normally think of them. Space is a vacuum. There is no air. Sound cannot travel through it. What we are hearing are translations. Electromagnetic signals converted into frequencies our ears can process. But the information encoded in those signals is real. The patterns, the variations, the rhythms. They tell us about the forces at work around Saturn, about the shape and strength of its magnetic field, about the charged particles spiraling along invisible lines of force, about the auroras blazing at the poles. Saturn is speaking in its own way, and what it says is strange. Let us go deeper now, into the interior, into the place where the pressure becomes so intense that the laws of chemistry begin to bend. We talked earlier about liquid metallic hydrogen, that vast underground ocean of compressed hydrogen that fills most of Saturn's volume. But there is something else happening down there, something that sounds like science fiction, but is increasingly supported by experimental evidence. It might rain diamonds inside Saturn. The idea is based on a simple chain of events. Saturn's atmosphere contains methane, a molecule made of one carbon atom bonded to 4 hydrogen atoms. High in the atmosphere, powerful lightning bolts strike the methane molecules and break them apart, freeing the carbon. This carbon then combines with itself, forming soot particles. These soot particles are carried downward by atmospheric currents into deeper, hotter, higher pressure regions. As they descend, the increasing pressure compresses the soot first into graphite, the same material found in pencil lead, and then, at even greater depths, the graphite is crushed into diamond. Solid diamond crystals forming inside the atmosphere of a gas giant. But the story does not end there. As the diamond crystals continue to fall, the temperature continues to rise. Eventually, roughly 8,000 degrees Celsius, the diamonds begin to melt. Liquid diamond, drops of molten carbon, denser than the surrounding atmosphere, raining downward through layers of compressed hydrogen gas toward the core of the planet. If you find yourself coming back to videos like this one to fall asleep, there's a reason. Your mind needs somewhere to go. Not music, not silence. Something steady to follow. Beyond the Stars is a full collection of overnight narrated space journeys. 5 tracks, 6 to 8 hours each. No ads, no endings, no interruptions. $39, once, any device. Link is in the description. We'll be back in a moment. A rain of liquid diamonds falling through a world where there is no ground. Just deeper and deeper layers of heat and pressure and darkness. Not everyone agrees this happens. Some scientists argue that the amount of soot produced by lightning is too small to generate significant diamond formation. Others suggest that at the extreme temperatures and pressures involved, the carbon might simply dissolve into the surrounding hydrogen rather than crystallizing into diamonds. The debate continues, but experiments performed at laboratories like the SLAC National Accelerator Laboratory at Stanford, using powerful lasers to recreate the conditions inside gas giant planets, have confirmed that diamond formation is at least possible under these conditions. The researchers watched tiny nanodiamonds form in real time as they subjected hydrocarbon materials to extreme compression. The physics works. Whether it happens at scale inside Saturn is still an open question. But the diamond rain is not the only exotic precipitation that might be falling deep within Saturn. There is also helium rain. This one is not speculative. There is now direct experimental evidence supporting it. Remember that Saturn radiates about 2.5 times more energy into space than it receives from the Sun. Jupiter does this too, but Jupiter's excess heat can be explained by the slow cooling of its interior since formation, a process called the Kelvin-Helmholtz mechanism. As a planet cools, its internal pressure drops slightly, and it contracts. This compression heats the core, releasing gravitational energy as thermal energy. For Jupiter, this explanation works. The math checks out. But for Saturn, it does not. Saturn is smaller than Jupiter. It should have cooled off faster. By now, its original reservoir of formation heat should have been largely exhausted. It should not be radiating this much extra energy. Something else must be generating heat inside Saturn. And the answer, scientists believe, is helium rain. Deep inside Saturn, the temperature is lower than inside Jupiter. And at those lower temperatures, helium does not dissolve as easily in liquid hydrogen. Think of it like trying to dissolve sugar in cold water versus hot water. In cold water, the sugar clumps together and sinks to the bottom. Inside Saturn, something similar happens with helium. The helium separates from the hydrogen and forms droplets. Heavy, dense droplets of liquid helium. And those droplets fall. They rain downward through the liquid metallic hydrogen, sinking toward the core. As the helium drops fall, they are compressed further by the planet's gravity. This compression converts gravitational potential energy into heat. The falling helium heats the interior, and that is where the extra energy comes from. Saturn's mysterious excess heat is generated by a slow, steady, silent rain of helium falling through its own interior. It is a furnace fueled by gravity and chemistry. And it has been burning for billions of years. This process also explains something else that puzzled scientists for decades. Saturn's atmosphere has less helium in it than expected. When compared to the Sun, which formed from the same cloud of gas and dust as the planets, Saturn's outer atmosphere is noticeably depleted in helium. The helium has not disappeared. It has simply sunk. It has rained out of the upper layers and settled deeper inside the planet. leaving the atmosphere lighter and less helium-rich than it should be. Experiments conducted at Lawrence Livermore National Laboratory in 2021 provided the first direct evidence for this process. Using powerful lasers, scientists compressed a mixture of hydrogen and helium to the pressures and temperatures found deep inside Saturn and Jupiter. They observed a sharp change in the mixture's electrical properties at certain conditions, a signature of the helium separating out. The helium rain is real. It happens at pressures between 60 and 180 gigapascals, which is millions of times the air pressure at Earth's surface. The conditions match what we expect to find inside Saturn, and the results confirmed predictions that scientists had been making since the mid-1970s. So picture this. Deep inside Saturn, beneath thousands of miles of cloud and gas and liquid hydrogen, there is a world of unimaginable pressure and heat, where metallic hydrogen flows like an ocean, where helium falls like rain, where diamonds may crystallize out of the darkness and melt before they reach the bottom. It is a place no human will ever visit. No probe will ever survive long enough to measure. We can only infer its existence from the faint gravitational tugs and magnetic whispers that reach the surface. Saturn's interior is a hidden kingdom, violent and alien, locked away from us forever. And yet, the interior is not the only part of Saturn that keeps its secrets. The planet's relationship with its moons reveals even more layers of mystery and terror. Saturn has 274 known moons. That number keeps growing. In 2025 alone, 128 new moons were discovered, bringing the total to nearly triple the number known just a few years earlier. Most of these moons are tiny, irregular chunks of ice and rock captured by Saturn's gravity at some point in the distant past, tumbling through orbits that are tilted, elliptical, and sometimes retrograde, meaning they orbit in the opposite direction from the planet's rotation. They are the scattered wreckage of an ancient gravitational battlefield. But among this swarm of small worlds, there are a few that stand out, and two of them are among the most remarkable objects in our entire solar system. The first is Titan, Saturn's largest moon, larger than the planet Mercury, the only moon in the solar system with a thick, substantial atmosphere. When the Cassini spacecraft arrived at Saturn in 2004, one of its primary missions was to study Titan, and what it found was astonishing. Titan is covered in a thick orange haze of nitrogen and methane. The atmosphere is so dense that you cannot see the surface from orbit in visible light. It is like trying to look through a foggy window. But when Cassini used radar and infrared instruments to peer through the haze, the picture that emerged was unlike anything scientists had expected. Titan has lakes, rivers, rain, clouds, seasons, a complete weather cycle, driven not by water, but by methane and ethane, hydrocarbons that exist as liquids on Titan's frigid surface, where temperatures hover around -179 degrees Celsius. The lakes are concentrated near Titan's poles, some of them larger than Earth's Great Lakes. The largest, called Kraken Mare, covers an area of roughly 154,000 square miles. That is nearly 5 times the size of Lake Superior. These are not water lakes. They are pools of liquid methane and ethane, dark and reflective under a sky that is permanently overcast with a thick, brownish haze. When it rains on Titan, it rains methane. Heavy drops of liquid hydrocarbon falling through a nitrogen atmosphere onto a landscape carved by the same processes that shape Earth's continents, just with a completely different chemistry. The Huygens probe, built by the European Space Agency and carried to Saturn aboard Cassini, descended through Titan's atmosphere on January 14, 2005. It was the first, and so far only landing on a world in the outer solar system. As it drifted down on its parachute, Huygens photographed the surface through the haze. The images showed river channels, drainage networks, shorelines. It looked eerily like Earth. When the probe finally touched down, it landed on a surface that was soft and slightly moist, perhaps a thin layer of hydrocarbon slush. The temperature was minus 179 degrees Celsius. The pressure was about 1.5 times that of Earth's surface, and the sky was a dim, murky orange. Titan is, in many ways, a frozen echo of early Earth. Its atmosphere is rich in nitrogen, just like ours. It has a methane cycle that mirrors our water cycle. Complex organic chemistry is happening in its upper atmosphere, driven by ultraviolet light from the sun, producing molecules called tholins, reddish-brown organic compounds that are thought to be similar to the building blocks of life. Some scientists have speculated that Titan could harbor a form of life that uses liquid methane instead of liquid water as its solvent. Such life would be fundamentally different from anything on Earth, a completely alien biochemistry. The idea remains theoretical, but the ingredients are there. The second remarkable moon is Enceladus. And if Titan is strange, Enceladus is one of the most exciting objects in the search for life beyond Earth. Enceladus is small, only about 300 miles across. You could drive across it in a few hours. Its surface is covered in bright, fresh ice, reflecting back over 90% of the sunlight that hits it. It is one of the most reflective bodies in the solar system, and for a long time, nobody paid much attention to it. Just another icy moonlet orbiting a gas giant. Nothing special. Then Cassini flew by and everything changed. In 2005, Cassini discovered jets of water vapor and ice particles erupting from long cracks near Enceladus's south pole. These cracks, nicknamed tiger stripes, were warm, much warmer than the surrounding ice. And from them, geysers of material were shooting hundreds of miles into space, at speeds of hundreds of meters per second. The plumes were so prolific that they supplied most of the material for Saturn's tenuous E-ring, the outermost of its major rings. But the real revelation came when Cassini flew directly through the plumes and sampled their contents. The spacecraft detected water, salt, silica nanoparticles, molecular hydrogen, and organic compounds. The salt and silica were particularly telling. They suggested that the water erupting from Enceladus had been in contact with a rocky sea floor, heated to high temperatures. The molecular hydrogen indicated hydrothermal activity, chemical reactions between hot rock and water at the bottom of an ocean. The same kind of hydrothermal vents that exist on the floor of Earth's oceans. The same vents that, on Earth, support thriving ecosystems of bacteria and strange creatures in total darkness, powered not by sunlight, but by chemical energy from the planet itself. Enceladus has a global ocean. Beneath its icy shell, a vast body of liquid water surrounds the entire moon, heated from below by tidal forces generated by Saturn's gravity. The ocean is estimated to be between 20 and 30 miles deep. It is warm enough to remain liquid. It contains the chemistry needed for life, and it is venting that water directly into space, making it one of the few places in the solar system where we could potentially sample an alien ocean without even having to drill through the ice. This is why, when Cassini's mission was ending in 2017, NASA chose to destroy the spacecraft by plunging it into Saturn's atmosphere, rather than risk it eventually crashing into Enceladus or Titan. They wanted to protect those moons, because if there is life there, even microbial life, we cannot risk contaminating it with Earth organisms that might have hitched a ride on the spacecraft. The decision to sacrifice Cassini was an act of planetary protection, a deliberate destruction of a working spacecraft to preserve the possibility of alien life on a moon no bigger than the state of Arizona. And so, Cassini fell. On September 15, 2017, the spacecraft fired its thrusters for one final maneuver, pointing its instruments towards Saturn as it plunged into the atmosphere at over 75,000 miles per hour. It transmitted data right up until the moment it was torn apart by friction and pressure, its bus-sized body breaking apart in Saturn's blue sky. A brief flash of heat, a puff of vapor, and then nothing. 20 years of exploration ended in seconds, as the spacecraft became part of the planet it had spent 13 years studying. Now, let us talk about something that does not get discussed enough. Saturn as a cosmic entity, not just a planet with rings and moons and storms, but Saturn as a force, a gravitational powerhouse whose influence extends far beyond its own orbit and shapes the architecture of the entire solar system. Saturn is massive, not as massive as Jupiter certainly, but with 95 times the mass of Earth, it exerts a gravitational pull that reaches deep into the surrounding space. And throughout the history of the solar system, that gravity has played a crucial role in determining where other objects ended up. In the early solar system, when the planets were still forming from the swirling disk of gas and dust around the young sun, Jupiter and Saturn engaged in a gravitational dance that reshaped everything. According to models like the NICE model and the Grand Tack hypothesis, the migration of Jupiter and Saturn through the early solar system scattered smaller bodies, redirected the orbits of asteroids and comets, and may even have determined the final positions of Uranus and Neptune. Some scientists believe that a specific orbital resonance between Jupiter and Saturn triggered a period of instability called the Late Heavy Bombardment, a catastrophic epoch roughly 4 billion years ago, when the inner solar system was pelted with a barrage of asteroids and comets, scarring the surfaces of the Moon, Mercury, and Mars. If this model is correct, then Saturn is partly responsible for the violence that shaped the early Earth, the impacts that delivered water to our planet, the collisions that may have contributed to the formation of our Moon, the bombardment that sterilized the surface and then, ironically, may have helped seed it with the ingredients for life. Saturn's gravity, working in tandem with Jupiter's, was one of the architects of the solar system we live in today, and Saturn's influence continues. Its gravity helps shepherd the asteroid belt, keeping it from coalescing into a planet. Its moons interact with its rings in complex ways, carving gaps, creating waves, and maintaining the sharp edges of the ring structures. The small moonpan orbits within the Encke gap, a narrow opening in the A-ring, and its gravity keeps the gap clear. The moon Prometheus orbits just inside the F-ring, pulling streamers of material from the ring's inner edge, creating kinks and knots and braids. The moon Daphnis orbits within the Keeler gap, and its gravity raises waves in the ring material on either side, like the wake of a boat passing through still water. These interactions are not just beautiful, they are laboratories. By studying how Saturn's moons sculpt its rings, scientists gain insights into the fundamental physics of disk dynamics, the same physics that governs the formation of planets around young stars, the same physics that shapes spiral galaxies. Saturn's ring system is a miniature model of a protoplanetary disk, right here in our own solar system, and the moons orbiting within it are analog planets, demonstrating in real time how gravity shapes matter in a rotating disk. But there is a darker implication too. Saturn's gravity is not just a sculptor, it is a destroyer. Objects that wander too close are torn apart. Moons that drift inward are consumed. The rings themselves are evidence of this destructive power. And the process is ongoing. Saturn is slowly pulling its rings inward. The ring rain we discussed earlier is a symptom of this gravitational appetite. Saturn is eating its own rings, particle by particle, year by year. The most iconic feature in our solar system is being devoured by the planet that wears it, and one day, probably within the next 100 million years, the rings will be gone. Saturn will be bare again, a golden gas giant orbiting silently in the outer solar system, with no visible reminder of the icy halo it once wore. Future astronomers, if there are any, will see only a smooth, featureless world, and they will have no way of knowing what they missed. Let us now return to the atmosphere, because there is one more mystery we need to explore, one that cuts to the very heart of what Saturn is. Saturn's magnetic field is peculiar. Almost every planet in the solar system that has a significant magnetic field has a tilt between its magnetic axis and its rotational axis. Earth's magnetic poles are offset from its geographic poles by about 11 degrees. Jupiter's magnetic field is tilted by about 10 degrees. But Saturn's magnetic field is almost perfectly aligned with its rotational axis. The tilt is less than 1 degree. This is extremely unusual. In fact, theoretical models suggest it should be impossible. The dynamo process that generates planetary magnetic fields requires some asymmetry, some unevenness, some tilt. Without it, the theory says the field should decay and disappear. And yet Saturn's field is strong, stable, and almost perfectly symmetric. One possible explanation is that there is a layer deep inside Saturn that acts as a kind of filter, smoothing out any asymmetry in the magnetic field before it reaches the surface. Some researchers have proposed that a stable, electrically conducting layer of helium settled out from the hydrogen above it could suppress the non-axisymmetric components of the field. In other words, the helium rain that generates Saturn's excess heat might also be responsible for the eerie perfection of its magnetic field. The same process that makes the planet warm also makes it magnetically strange. But this explanation raises its own questions. If the helium layer is filtering the field, then what does the unfiltered field look like deeper inside? Is it tilted like other planets? Is it chaotic? Is it something we have never seen before? We cannot know. The layer shields us from the deeper truth. Saturn's magnetic symmetry is, in a sense, a mask. And behind that mask, we have no idea what the planet is really doing. Cassini tried to measure this. During its grand finale orbits, when it passed between the planet and the rings, it got closer to Saturn's magnetic field than any spacecraft ever had. And the data it returned confirmed the near-perfect alignment. But it also revealed something unexpected. The magnetic field was not entirely featureless. There were subtle variations, small ripples and asymmetries that hinted at a more complex picture beneath the surface. Scientists are still analyzing this data, years after Cassini's death. The planet gave up a few of its secrets in those final weeks, but not all of them. Now, let us step back, way back. Let us look at Saturn not as a collection of features and mysteries, but as a single entity, a world. What is Saturn really? What role does it play in the grand architecture of our solar system? And what does it tell us about ourselves? Saturn is often described as a failed star. This is not quite accurate, but it captures something important. Like the Sun, Saturn is made mostly of hydrogen and helium. It formed from the same primordial cloud of gas and dust. It even has some of the same internal processes, like convection and compression and heat generation. But it never gathered enough mass to ignite nuclear fusion in its core. It is about 80 times too light for that. If you could somehow dump enough hydrogen onto Saturn to increase its mass by a factor of 80 or so, it might ignite and become a red dwarf star. Our solar system would be a binary system. 2 stars. And everything about our cosmic neighborhood would be different. But Saturn did not ignite, it cooled. It settled into its orbit, and it became something else, a guardian of sorts. Its gravity, combined with Jupiter's, acts as a shield for the inner solar system. The 2 gas giants deflect or capture many of the comets and asteroids that drift inward from the outer reaches of the solar system. Without them, Earth would be bombarded far more frequently. The impact rate would be higher. The environment would be less stable. Life as we know it might never have had the chance to evolve. There is a school of thought in astrobiology that suggests gas giants in the outer regions of a star system are a prerequisite for the development of complex life on rocky inner planets. They are the bouncers at the door, turning away most of the dangerous objects before they reach the habitable zone. Saturn plays this role quietly. It does not get the credit Jupiter does. Jupiter is louder, brighter, more dramatic, but Saturn is there, watching, pulling, redirecting. A silent sentinel in the cold outer reaches of our solar system. And yet, calling Saturn a guardian makes it sound benevolent. It is not. Saturn is indifferent. It is a ball of hydrogen and helium obeying the laws of physics. It does not care about Earth. It does not care about life. If a comet that Saturn deflected happened to be redirected toward Earth instead of away from it, Saturn would not hesitate. It does not think. It does not choose. It simply exists, and its existence shapes the trajectories of everything around it, for better or worse. This is the real terror of Saturn, not the storms, not the pressure, not the diamond rain or the hexagonal jet streams or the disappearing rings. The real terror is the scale, the sheer, incomprehensible scale of a world so large and so powerful that it bends the fabric of the solar system around it. And it does all of this without any intention, without any awareness, without any regard for the tiny, fragile, watery world orbiting billions of miles away, where creatures made of carbon and water have spent a few thousand years looking up at the sky and wondering what those lights mean. Saturn does not know we exist. It does not know anything. And in the vast timeline of the solar system, the period during which humans have been watching Saturn is so brief that it barely registers. Saturn has been there for 4.5 billion years. Humans have been looking at it for maybe 5,000. That is 1/1,000,000th of Saturn's lifetime. We are a blink, a momentary flash of consciousness in a universe that does not require our presence and will not notice our absence. And yet, here we are, building spacecraft, launching them across billions of miles of empty space, sending them into orbit around a gas giant to take pictures and measure fields and taste the plumes of alien oceans. We are small. We are fragile. We live on a speck of rock in the habitable zone of an ordinary star. And still, we reached Saturn. We touched its moons. We dove through its rings. We listened to its voice. That is remarkable. That is the other side of the terror, the awe, the recognition that we are capable of understanding, at least in part, things that are vastly larger and more powerful and more ancient than ourselves. Let us go back to the rings one more time, because there is one more thing about them that deserves attention, and it might be the strangest detail of all. Saturn's rings are disappearing. We covered that. Ring rain is pulling material inward. The rings will be gone in 100 million years or so. But here is what is strange. If the rings are only a few 100 million years old, and they are going to be gone in another 100 million years, then the total lifespan of Saturn's ring system is somewhere between 300 million and 500 million years. Saturn is 4.5 billion years old. That means the rings exist for only about 5 to 10% of the planet's total lifetime. We just happen to be alive during that window. We happen to be observing Saturn at the exact moment in its history when it has rings. What are the odds of that? Think about it. If you were going to pick a random moment in Saturn's 4.5 billion year existence to observe it, the chances of catching it with rings are roughly 1 in 10, maybe 1 in 20. We got lucky, extraordinarily lucky. Or maybe it is not luck at all. Maybe Saturn has had rings before. Maybe the destruction of a moon or the capture of a comet happens more than once over the life of a planet. Maybe ring systems come and go, forming and disappearing multiple times over billions of years. If that is the case, then the current rings are just the latest chapter in a long history of temporary decoration. Saturn has worn many crowns. This is just the one we get to see. Some researchers have proposed exactly this, that ring formation events might be periodic, driven by the gravitational interactions between Saturn's moons. Over millions of years, the orbits of moons can shift. They can be nudged by resonances with other moons. They can migrate inward, closer to Saturn. And if a moon crosses the Roche limit, it is torn apart. Its remains become a new ring. The process could have happened multiple times in Saturn's past. Each time, the resulting ring system would eventually dissipate, raining back onto the planet. And each time, the gravitational dynamics of the remaining moons would slowly set up the conditions for another moon to fall. If this is true, then Saturn's rings are not a singular event. They are a cycle, a rhythm, a repeating pattern of creation and destruction played out over geological timescales. And we are witnessing just one beat of that rhythm. Let us talk about time, because Saturn forces us to confront time in a way that most celestial objects do not. A day on Saturn is short, about 10 hours and 34 minutes. The planet spins so fast that its equator bulges outward, making Saturn the flattest planet in the solar system. Its polar diameter is only about 90% of its equatorial diameter. If you could look at Saturn from the side, you would see that it is noticeably squashed, like someone sat on a beach ball. But a year on Saturn is long, about 29.5 Earth years each. Season on Saturn lasts more than 7 Earth years. When Cassini arrived at Saturn in 2004, it was early winter in the northern hemisphere. By the time the spacecraft was destroyed in 2017, it was approaching northern summer solstice. Over the course of 13 years, Cassini watched Saturn transition through nearly half a Saturnian year. It observed the hexagon emerge from winter darkness into spring sunlight. It watched the rings change appearance as the angle of sunlight shifted. It tracked storms and cloud patterns as the seasons slowly turned. This is one of the reasons Saturn feels so alien, not just because of its size or its composition, but because of its pace. Everything on Saturn happens slowly, by our standards. Its seasons last for years. Its megastorms build over decades. Its rings are disappearing over hundreds of millions of years. Even the helium rain inside it is a process that has been ongoing for billions of years. Saturn operates on timescales that are almost incomprehensible to a species that considers a century to be a long time. When we look at Saturn, we are looking at a world that is patient in a way we will never be. A world that does not rush, that does not hurry, that lets its processes unfold with the slow, grinding certainty of gravity and thermodynamics. The storms come when they come. The rings fall when they fall. The helium sinks when it sinks. There is no urgency on Saturn. There is only physics, operating at its own pace, indifferent to our desire to understand it quickly. And this brings us to one of the deepest questions that Saturn raises. A question about our place in the universe, about the meaning of observation itself. When Galileo first pointed his crude telescope at Saturn in 1610, he saw something that confused him. 2 bumps on either side of the planet. He described them as handles or perhaps large companion bodies flanking the planet. He had no framework to understand what he was seeing. The idea of rings around a planet had never occurred to anyone. 45 years later, Christian Huygens figured it out. He announced, in a coded anagram that he later deciphered, that Saturn was surrounded by a thin, flat ring, nowhere touching the body of the planet. It was a revolutionary insight, and it was only the beginning. Over the next 4 centuries, our understanding of Saturn deepened exponentially. Better telescopes revealed the Cassini division, the gap between the A and B rings. Spectroscopy told us what the rings were made of. Spacecraft visits, first Pioneer 11 in 1979, then Voyagers 1 and 2 in 1980 and 1981, and finally Cassini from 2004 to 2017, revealed a world of staggering complexity. Each visit peeled back another layer. Each new instrument detected something unexpected, and every answer generated 10 new questions. We know more about Saturn now than at any other point in human history, and yet, in a profound sense, we know almost nothing. We do not know what happens at the core. We do not know what created the rings. We do not know why the hexagon exists. We do not know what generates the spokes. We do not know whether there is life in the ocean beneath Enceladus. We do not even know the exact length of Saturn's day, because the planet has no solid surface, and its different layers rotate at different speeds, and the seemingly symmetrical magnetic field gives us no fixed reference point. For years, scientists measured Saturn's rotation using radio emissions, but then Cassini discovered that the radio period had changed since Voyager. Saturn's day had apparently gotten longer. Or perhaps the radio emissions were not measuring the rotation at all, but something else entirely. The mystery persists. Saturn humbles us. It reminds us that despite all our technology, all our instruments, all our models and simulations and theoretical frameworks, the universe is far larger and far stranger than we can fully grasp. Saturn is right there, in our own solar system, one of 8 planets orbiting our own star, and it is full of things we cannot explain. Imagine what lies beyond. In the thousands of exoplanet systems we have discovered so far, on the gas giants orbiting other stars, where we have no spacecraft, no close-up images, no way to taste the plumes or listen to the radio emissions. If our own neighborhood contains something as bizarre and beautiful and terrifying as Saturn, what might be out there, circling stars we cannot even see with the naked eye? Let us come back now to the immediate, to the physical, to the things we can observe and measure and struggle to understand. Saturn's south pole, we mentioned it briefly, the vortex there. But let us look closer. The south polar vortex on Saturn is a monster. It was first observed in detail by Cassini in 2006, and the images were startling. The vortex has a well-defined eye, remarkably similar to the eye of a hurricane on Earth. Warm air descends in the center, creating a clear spot surrounded by towering walls of cloud. The eye is roughly 8,000 kilometers wide. The winds at the eye wall reach speeds of over 550 kilometers per hour. And unlike Earth hurricanes, which move across the ocean surface and eventually dissipate when they lose their energy source, Saturn's south polar vortex is stationary. It sits at the pole. It does not wander. It does not weaken. It is locked in place by the planet's rotation and sustained by processes in the deep atmosphere that we are still trying to understand. The eye of this vortex is one of the most visually dramatic features in the entire solar system. Images from Cassini show swirling cloud walls dropping away into a dark center, lit from the side by the distant sun. It looks like a portal, a doorway into the planet itself, and in a sense, it is. The descending air in the vortex eye provides a rare window into deeper atmospheric layers that are normally hidden from view. Scientists use Cassini's instruments to peer into this opening and measure temperatures and compositions at levels they could not normally reach. What they found was consistent with the picture we have been building. A complex layered atmosphere, bands of different chemical compositions, temperature inversions, regions of unexpected warmth and unexpected cold. Saturn's atmosphere is not simple. It is a multi-layered onion of chemistry and physics, and each layer has its own story to tell. And there is something else about Saturn's atmosphere that deserves mention. Something that connects back to the question of whether Saturn is truly the scariest planet in our solar system. Saturn has lightning. We mentioned this in the context of the Great White Spot. But let us dig deeper. Saturn's lightning is not like Earth's lightning. On Earth, lightning is generated by the buildup of static charge in thunderstorm clouds. When ice particles and water droplets collide and separate charge within the cloud, the resulting discharge can carry a peak current of around 30,000 amperes and heat the surrounding air to 30,000 degrees Celsius. It is dramatic and powerful by human standards. Saturn's lightning is on a different level entirely. The discharges detected by Cassini were thousands of times more energetic than anything produced on Earth. The radio bursts associated with Saturn's lightning, called Saturn electrostatic discharges or SEDs, were so powerful that they could be detected from millions of miles away. Each discharge lasted for fractions of a second, but released an enormous amount of electromagnetic energy. During major storms, these discharges occurred continuously, one after another, creating a relentless barrage of electrical energy deep within the cloud layers. And unlike Earth, where lightning occurs in relatively small localized thunderstorms, Saturn's lightning is associated with enormous storm systems that can span thousands of miles. The 2010 Great White Spot produced lightning at a rate of 10 discharges per second. Each one was a titanic event, and collectively, the power released by the storm's lightning and convective activity was a significant fraction of Saturn's total radiated power. The storm was not just weather, it was a planetary scale energy release. In 2009, Cassini even managed to capture the first images of lightning on Saturn. Brief flashes of light, visible against the dark night side of the planet, illuminating clouds from within. Each flash covered an area of about 300 kilometers. These were not small sparks. They were explosions of light buried deep within the atmosphere, powerful enough to be photographed from orbit. The storms that produce this lightning are driven by the same water-based convection that triggers the Great White Spots. Deep inside Saturn's atmosphere, at pressures of 10 to 20 bars, Water exists as a vapor. When conditions align, this water vapor rises explosively, condensing and releasing enormous amounts of latent heat. This heat drives the convection even harder, creating a runaway process that powers the storm for months. The lightning is a byproduct of this convective violence, generated as ice and liquid particles collide in the rising plumes. There is something deeply unsettling about the scale of violence happening inside Saturn's atmosphere. We look at this planet and see a golden sphere with pretty rings, but beneath that surface, there are explosions of electricity thousands of times more powerful than anything on our planet. There are storms that wrap around the entire world. There are winds that never stop and pressure that never relents. Saturn is not quiet. It is screaming. We just cannot hear it from here. And now, let us consider one more layer of this planet's strangeness. Saturn's rotation. Determining how fast Saturn spins should be straightforward. For a rocky planet like Earth, you measure the rotation of the solid surface. For a gas giant like Jupiter, where there is no solid surface, you measure the rotation of the magnetic field, since the magnetic field is generated by the spinning of the planet's metallic interior and should rotate at the same rate as the core. When Voyager 1 flew by Saturn in 1980, it measured the periodicity of Saturn's radio emissions and derived a rotation period of 10 hours, 39 minutes, and 24 seconds. This became the accepted length of Saturn's day. It was used in scientific models and textbooks for over 2 decades. But when Cassini arrived and began measuring those same radio emissions, something was wrong. The period had changed. It was now about 10 hours and 45 minutes. Saturn's day had apparently gotten 6 minutes longer in the span of 20 years. This makes no sense for a solid body. A planet's core does not suddenly slow down. The change was too large to be explained by any known physical mechanism acting on the interior. So what was going on? The answer, scientists eventually concluded, is that Saturn's radio emissions do not perfectly track the rotation of the core. They are influenced by the magnetosphere, which in turn is affected by the solar wind, Saturn's seasons, and the distribution of plasma in the planet's environment. The radio emissions are telling us about the magnetic environment, not the true rotation rate. And the magnetic environment changes. It fluctuates. It is modulated by external factors that have nothing to do with how fast the planet is actually spinning. So how fast does Saturn really spin? It is surprisingly hard to say. Different measurement techniques give slightly different answers. Gravity field measurements from Cassini suggest a rotation period close to the original Voyager value, about 10 hours and 33 minutes, but there is still uncertainty. Saturn, a planet we have been studying with spacecraft for over 40 years, cannot tell us precisely how long its own day is. The planet keeps this information locked away, hidden behind the veil of its perfectly symmetric magnetic field and the confusing variability of its radio emissions. Compare this to Jupiter, where the tilted magnetic field provides a clear, stable signal that tracks the rotation of the core with high precision. Jupiter announces its rotation proudly, like a lighthouse beam sweeping across the darkness. Saturn whispers. It hides. It obscures. This is a theme with Saturn. Over and over, the planet presents a smooth, calm exterior that conceals a turbulent, mysterious interior. The bland-looking atmosphere that hides supersonic winds and planet-encircling storms. The perfect magnetic symmetry that masks a chaotic dynamo. The beautiful rings that are actually debris from a catastrophe. The peaceful-looking moons that harbor alien oceans and geysers of salt water. Saturn is a planet of deception. Nothing about it is what it first appears to be. Let us explore one more deception, one that speaks to the very nature of the rings themselves. When you look at Saturn's rings in high resolution, you see structure. Lots of structure. Thousands of individual ringlets, each one a narrow band of particles orbiting at a slightly different distance from the planet. Gaps, divisions, bright regions and dark regions, waves and ripples and corrugations. The detail is extraordinary. And much of it is created by the gravitational influence of Saturn's moons. When a ring particle orbits Saturn at a distance, where its orbital period is a simple fraction of a moon's orbital period, a resonance occurs. For example, a particle that orbits Saturn exactly twice for every orbit of the moon. Mimas is in a 2-to-1 resonance with Mimas. At this location, the gravitational pull of Mimas gives the particle a regular periodic tug in the same direction. Over time, these tiny tugs add up. They can clear particles out of a region entirely, creating a gap, or they can compress particles together, creating a dense ringlet, or they can set up spiral waves that propagate through the ring like ripples on a pond. The Cassini division, the largest gap in the main rings, is maintained by a 2-to-1 resonance with Mimas. The Encke gap in the A ring is kept clear by the small moon Pan, which orbits within the gap itself. The Keeler gap is maintained by the tiny moon Daphnis. Each gap, each edge, each wave pattern in the rings is a signature of a gravitational interaction. The rings are not passive. They are a dynamic system, constantly being sculpted by the gravitational forces around them. And some of those forces come not from the moons, but from inside Saturn itself. During the Cassini mission, scientists discovered that certain wave patterns in the rings were being driven by oscillations in Saturn's interior. The planet itself was ringing, vibrating at specific frequencies, and those vibrations were imprinting themselves on the rings, like the needle of a seismograph tracing an earthquake. By studying these waves, scientists could probe the internal structure of Saturn, using the rings as a natural detector. It was like listening to the planet's heartbeat through its own jewelry. These seismological discoveries revealed that Saturn's interior is more complex than previously thought. The boundary between the molecular hydrogen envelope and the deeper metallic hydrogen layer is not a sharp transition. It is gradual, blurred, extending over a wide range of pressures and temperatures. And the core itself may not be a discrete solid ball of rock and ice. It might be diluted, with heavy elements mixed into the surrounding hydrogen in a fuzzy, extended region. Saturn's interior is not neatly layered like an onion. It is more like a gradient, a smooth transition from gas to liquid to metal to rock, with no clear boundaries. This matters because it changes how we think about planet formation. For decades, the standard model of gas giant formation assumed that a rocky core forms first, and then gravity pulls in a thick envelope of hydrogen and helium gas from the surrounding disk. This model predicts a well-defined core surrounded by distinct layers. But if Saturn's core is fuzzy and diluted, it suggests that the formation process might have been more violent and chaotic than we imagined. Perhaps the core was partially dissolved by the energy released during the rapid accretion of gas. Perhaps impacts from large objects during the planet's youth mixed the core material upward into the envelope. The details are still being worked out. The point is that Saturn is forcing us to revise our models, not just of Saturn itself, but of how planets form in general. And since gas giants are the most common type of large planet found around other stars, understanding Saturn's interior has implications that reach far beyond our own solar system. Let us also talk about Saturn's smaller moons, because they are fascinating in their own right, and they add yet another layer of complexity to this already complicated world. We mentioned the 274 moons. Many of them are tiny, irregular, unremarkable at first glance, but some of them are deeply strange. Take Hyperion, a moon about 170 miles across, shaped like a potato and covered in deep craters that make it look like a sponge. Its density is so low that scientists believe it is more than 40% empty space. A porous, spongy body tumbling chaotically through space around Saturn. Its rotation is not regular. It does not spin at a constant rate or on a fixed axis. Instead, it tumbles unpredictably like a football thrown with a bad spiral. Scientists call this chaotic rotation, and Hyperion is one of the few objects in the solar system known to exhibit it. Then there is Iapetus, a moon about 900 miles across, famous for its extraordinary two-toned appearance. One hemisphere is dark, almost black, with a reflectance similar to charcoal. The other hemisphere is bright, almost as white as snow. The contrast is so extreme that when Giovanni Cassini discovered the moon in 1671, he could only see it on one side of Saturn. When it moved to the other side, its dark hemisphere was facing Earth, and it vanished from view. For years, Cassini thought the moon only existed on one side of Saturn's orbit. The reason for this dual appearance took centuries to unravel. The leading explanation involves a complex interplay between Iapetus's slow rotation, its orbit, and dust from Saturn's outer moon Phoebe. Phoebe orbits Saturn in a retrograde direction, and tiny particles knocked off its surface spiral inward towards Saturn. Iapetus, orbiting in the normal direction, runs into this dust face first, accumulating a dark coating on its leading hemisphere. The dark material absorbs more sunlight, warming that hemisphere. This warmth causes any surface ice to sublimate and migrate to the cooler, brighter trailing hemisphere, making the contrast even more extreme. A runaway feedback process called thermal segregation. Simple physics, extraordinary result. And then there is the equatorial ridge, a massive mountain chain running along Iapetus's equator, reaching heights of up to 13 miles. That is more than twice the height of Mount Everest. The ridge is unique in the solar system. Nothing else like it exists anywhere. Some scientists think it might be the remnant of a ring that Iapetus once had, which collapsed onto the surface. Others suggest it formed during a period of rapid spin early in the moon's history, when the equatorial bulge was frozen in place as the moon cooled and solidified. The origin of the ridge remains debated, and there is Mimas, the smallest body in the solar system, known to be rounded by its own gravity. It is only about 250 miles across. Its most prominent feature is a giant crater called Herschel, about 80 miles wide, covering nearly a third of the moon's diameter. The impact that created Herschel came close to shattering Mimas entirely. The crater gives the moon an uncanny resemblance to the Death Star from Star Wars, a coincidence that scientists and science fiction fans both appreciate. But beneath its battle-scarred surface, Mimas may be hiding something unexpected. Recent analysis of subtle variations in Mimas's orbital wobble suggests that it might have an internal ocean, a liquid water ocean beneath the ice, similar to Enceladus. If confirmed, this would mean that even a small, heavily cratered moon in the shadow of Saturn's rings could be geologically active and potentially habitable. Each of Saturn's moons adds a piece to the puzzle. Together, they form a miniature solar system of their own, a complex gravitational dance of dozens of worlds, each one influenced by the others, each one shaped by its relationship to the giant planet at the center. Studying Saturn's moons is like studying planetary science in microcosm. The same processes that shape planets around stars, tidal heating, orbital resonances, material exchange, atmospheric evolution, all happen here, on a smaller scale, within reach of our instruments. And it is through these moons that Saturn may ultimately prove most important to the biggest question of all, the question of whether life exists beyond Earth. Enceladus, with its saltwater ocean and hydrothermal vents, is one of the top candidates. Titan, with its complex organic chemistry and liquid methane seas, is another. Even Mimas, with its possible hidden ocean, cannot be ruled out. The Saturn system is not just a collection of worlds. It is a laboratory for astrobiology, a testing ground for our theories about where life can emerge and what conditions it requires. If we ever find life in the Saturn system, it will transform our understanding of the universe. It will tell us that life is not a rare accident, that given the right conditions, the right chemistry, the right energy source, biology can emerge even in the cold, dark, radiation-soaked environs of a gas giant's orbit. It will mean that the universe is probably teeming with life, that the silence of the cosmos is not evidence of absence but of distance, of the vastness of space and the limitations of our instruments. And if we look and find nothing, if we explore Enceladus and Titan and Mimas and all the other moons and find only ice and rock and chemistry without biology, that too will be profoundly important. It will tell us something about the rarity of life, about the extraordinary chain of events that had to occur on Earth for us to exist, about how special this pale blue dot really is. Either way, Saturn will be at the center of the answer. Let us now return to the planet itself, and let us consider something we have not yet addressed directly: the density of Saturn. Saturn is less dense than water. This is one of those facts that sounds like a joke, but is completely true. The average density of Saturn is about 0.69 grams per cubic centimeter. Water is 1 gram per cubic centimeter. If you could somehow find a bathtub large enough and fill it with water, Saturn would float. The planet that is 75,000 miles wide, 95 times the mass of Earth, wrapped in rings of ice and orbited by hundreds of moons. It would bob on the surface like a beach ball. This low density is a consequence of Saturn's composition. It is almost entirely hydrogen and helium, the two lightest elements in the universe. Even though the pressure at its core is immense, the vast majority of Saturn's volume is occupied by relatively low-density gas and liquid. The core itself is dense, yes, but it makes up a small fraction of the total mass. The rest is hydrogen, spread out over an enormous volume, giving the planet a bulk density lower than that of any liquid you would encounter on Earth. This fact is worth sitting with for a moment, because it tells us something about the nature of giant planets. They are not solid, they are not dense, they are diffuse, tenuous, extended. Saturn is enormous, but it is made of almost nothing. Thin gas compressed into thick liquid, layered over a small, hot core. If you could somehow compress Saturn down to the density of Earth, it would fit inside a sphere far smaller than you might expect. And if you could somehow expand Earth to the density of Saturn, our planet would be a massive, fluffy cloud of rock vapor, larger than any world in our solar system. Size and mass and density are not the same thing. Saturn teaches us this lesson in the most dramatic way possible. The second largest planet in our solar system, made of the lightest materials, floating on water, dense enough at its core to crush diamond, thin enough in its atmosphere to barely register as matter at all. A paradox wrapped in golden clouds. And now let me take you on one more journey. This one is imaginary, but it is grounded in everything we know. Imagine you are falling towards Saturn. You are in a spacecraft, small and fragile, descending into the atmosphere. You pass the rings first. Up close, they are nothing like the smooth, continuous bands they appear to be from a distance. They are a blizzard of ice. Chunks and particles and boulders of water ice, tumbling past, you on all sides, each one following its own orbit around the planet. Some are as small as snowflakes. Others are as large as houses. They catch the dim sunlight and glitter against the black sky. It is beautiful, and it is dangerous. A single collision with one of the larger particles could end your mission. You clear the rings and enter the upper atmosphere. The gas is thin here, almost nothing. Just a faint whisper of hydrogen and helium and traces of methane. The sky above you is dark. The stars are still visible, but the planet is below you now. A vast, curved horizon of hazy gold, stretching in every direction. You cannot see the surface because there is no surface. Just cloud, layer upon layer of cloud, descending into darkness. As you fall deeper, the atmosphere thickens. The temperature begins to rise. The pressure increases. The clouds change. First, ammonia ice crystals, white and cold. Then ammonium hydrosulfide, brown and acrid. Then water ice, clear and heavy. Each layer is its own world, with its own chemistry, its own temperatures, its own weather patterns. The wind is constant, howling past your spacecraft at hundreds of miles per hour. You are not falling straight down. You are being swept sideways, carried along by jet streams that never stop. The sky above you gradually fades from black to deep blue to a murky brown as the atmosphere becomes too thick for starlight to penetrate. It is getting warm now. The pressure is building. Your instruments are straining. The hydrogen around you is no longer a gas. It is a supercritical fluid, a state of matter that is neither truly gas nor truly liquid, but something in between, dense, viscous, pressing against the hull of your spacecraft like an invisible hand. Deeper, the temperature climbs past 1,000 degrees. The pressure is hundreds of thousands of times Earth's atmosphere. The hydrogen is fully liquid now, not water-like liquid. This is dense, heavy, compressed liquid hydrogen, hot enough to glow faintly in the infrared. Your spacecraft groans. The hull flexes. The instruments begin to fail. You can no longer see anything. There is no light here, no horizon, no sky, just pressure and heat and the slow, crushing embrace of a planet-sized ocean of hydrogen. And then the transition happens. At a depth of about 20,000 kilometers below the cloud tops, the liquid hydrogen undergoes a phase change. The atoms are pressed so tightly together that the electrons break free and begin to flow between them. The hydrogen becomes metallic, conductive, a liquid metal ocean thousands of miles deep, conducting electricity and generating the magnetic field that wraps around the entire planet. This is the engine room of Saturn, the powerhouse, the source of its magnetic shield, and you have reached it, in your imagination at least, at a depth where no real spacecraft could survive. But the descent is not over. Below the metallic hydrogen is the core, hot, dense, probably a mixture of rock, ice, and heavy elements, compressed to incredible density. The temperature here approaches 21,000 degrees. The pressure exceeds 10 million times Earth's atmosphere. The conditions are so extreme that the behavior of matter is barely understood. We can model it, we can simulate it, but we have never directly measured it. This is the heart of Saturn, a place of fire and pressure and absolute darkness, buried beneath thousands of miles of gas and liquid and metal. It has been there since the planet formed, 4.5 billion years ago, and it will remain there for billions of years to come, slowly cooling, slowly releasing its heat, slowly raining helium into its own interior, while the world above it churns with storms and hexagons and disappearing rings. You will never make that journey. No human ever will, not in our lifetime, probably not in 1,000 lifetimes. The distances are too vast. The conditions are too extreme. The technology required to survive even the upper layers of Saturn's atmosphere does not exist. And the deeper you go, the more impossible it becomes. Saturn's interior is one of the most hostile environments in the known universe. It is a place defined entirely by force, by gravity pulling inward, by pressure building from above, by heat radiating from below. There is no room for fragility there, no room for biology, no room for anything that is not made of hydrogen or helium or the compressed remnants of the solar system's birth. And yet, we know it is there. We can measure its effects. We can see the magnetic field it generates. We can detect the heat it releases. We can hear, in the converted radio emissions, the echo of the processes happening far below the clouds. Saturn's core is hidden, but it is not silent. It speaks through its gravity, through its magnetism, through the subtle wobble of its moons and the delicate waves in its rings. Every measurement we make of Saturn's exterior tells us something about what lies within. We are reading the surface of the planet like a doctor reads a patient's skin, looking for clues about the organs underneath. This is one of the great achievements of planetary science, the ability to infer the invisible from the visible, to deduce the structure of a planet's interior from measurements made millions of miles away. It requires math, physics, creativity, patience, and a willingness to accept that some questions may never be fully answered. Saturn rewards curiosity, but it also demands humility. Every time we think we have figured something out, the planet reveals another layer of complexity that forces us to reconsider. Let us now talk about the future, because the story of Saturn is far from over. As of now, there is no spacecraft orbiting Saturn. Cassini was the last. Since its destruction in 2017, we have been studying Saturn from a distance, using ground-based telescopes, the Hubble Space Telescope, and the James Webb Space Telescope, and these instruments have continued to reveal new things. In 2023, the James Webb Space Telescope turned its infrared eye towards Saturn and captured images that were unlike anything we had seen before. In the infrared, Saturn's atmosphere appeared dark because methane in the upper atmosphere absorbs most of the reflected sunlight at those wavelengths. But the rings blazed brightly. They stood out against the dark planet like a crown of light. And the images revealed details about the ring structure, the atmospheric composition, and the seasonal changes that were previously invisible. Webb also detected features in Saturn's stratosphere that Cassini had not fully mapped, including temperature variations and chemical signatures that are helping scientists understand how energy moves through the upper atmosphere. But the real excitement is about what comes next. Several mission concepts are being developed to return to the Saturn system, and the primary target is not Saturn itself. It is Enceladus. The discovery of Enceladus's ocean and hydrothermal activity was one of the most consequential findings of the Cassini mission. And scientists are desperate to go back, not just to fly by, not just to orbit, but to fly through the plumes again, with instruments specifically designed to detect signs of life. amino acids, complex organic molecules, patterns of chemistry that cannot be explained by geology alone. The signatures of biology. One proposed mission, called the Enceladus Orbilander, would orbit Enceladus and eventually land on its surface near the tiger stripe fractures, sampling the material that rains back down from the plumes. Another concept involves a dedicated plume fly-through mission, equipped with next-generation mass spectrometers capable of analyzing the composition of the plume material with far greater sensitivity than Cassini's instruments could achieve. These missions are still in the planning and proposal stages, but the scientific community is united in the view that Enceladus is one of the most important targets for future exploration. If there is life in the outer solar system, Enceladus is the most accessible place to look for it. Titan II is a target. NASA's Dragonfly mission, a rotorcraft lander designed to fly through Titan's thick atmosphere, is scheduled to launch in the coming years. Dragonfly will explore Titan's surface, hopping from location to location, studying the chemistry of the dunes, the lakes, and the organic-rich terrain. It will look for prebiotic chemistry, the molecular building blocks that, on Earth, led to the emergence of life. Titan is too cold for water-based life as we know it. The surface temperature sits at roughly -179 degrees Celsius, far below the freezing point of water. At those temperatures, water ice is as hard as granite. It forms the bedrock of Titan's landscape, the mountains and ridges and crater rims. But methane and ethane, which are gases on Earth, exist as liquids on Titan. They fill the lakes, they carve the channels, they fall as rain and evaporate back into the haze. The chemistry of Titan's upper atmosphere is particularly fascinating. Ultraviolet light from the sun breaks apart nitrogen and methane molecules high above the surface. The fragments recombine in complex ways, forming a cascade of increasingly elaborate organic molecules. Hydrogen cyanide, acetylene, ethylene, benzene, and the tholins we mentioned, those reddish-brown organic compounds that give Titan its distinctive color and that drift downward like snow, settling onto the surface in a thin, sticky layer. These tholins are of enormous interest to astrobiologists because they are chemically similar to the organic compounds found in carbonaceous meteorites, the same meteorites that are thought to have delivered the raw ingredients for life to the early Earth. Titan is, in a sense, a frozen time capsule of prebiotic chemistry. The conditions on its surface and in its atmosphere resemble what scientists believe early Earth looked like before life emerged, roughly 4 billion years ago. The major difference is temperature. On Earth, those organic molecules dissolved in warm liquid water and eventually gave rise to the first living cells. On Titan, they sit in a deep freeze, preserved but inert. Or are they? Some theoretical models suggest that exotic forms of chemistry could operate in liquid methane, potentially giving rise to cell-like structures called azotosomes, membranes made of nitrogen-bearing compounds that could function in cryogenic conditions. This remains highly speculative, but it is not impossible. And Titan is the only place in the solar system where we could test the idea. Dragonfly will help answer some of these questions, but its rich organic chemistry also makes Titan a natural laboratory for understanding how complex molecules form and interact in environments very different from our own. Between Webb observations from afar and future missions up close, the next few decades promise to deepen our understanding of Saturn and its moons dramatically. We are at the beginning of a new chapter. Cassini was the prologue. The real story is about to unfold, but let us not get ahead of ourselves. Let us stay with Saturn a little longer, because there is something about this planet that transcends the individual facts and discoveries, something that is harder to articulate but equally important. Saturn changes you, not physically, not chemically, but cognitively. When you spend time thinking about Saturn, really thinking about it, something shifts in your perspective. The storms that last for decades, the winds that scream forever, the rings that are born from catastrophe and fade into nothing, the moons that hide oceans, the core that no one will ever see, the rain of diamonds and helium, the hexagonal jet stream that should not exist, the eerie radio songs, the lightning that dwarfs anything on Earth, the sheer, overwhelming scale of a world that is 95 times as massive as ours and made of almost nothing but hydrogen. When you sit with all of that, when you let it settle into your understanding, something happens. The world you live in starts to feel different. Not smaller, exactly, but more specific, more contingent, more fragile. Earth is not the default state of a planet. Earth is the exception. A rocky world with liquid water on its surface, a breathable atmosphere, a magnetic field strong enough to shield it from the solar wind, a moon large enough to stabilize its axial tilt, and a position in the solar system protected by gas giants that deflect the worst of the incoming debris. Every one of those conditions is unusual. Every one of them could have gone differently. And if any of them had, we would not be here. Saturn does not think about this. Saturn does not think at all. It just spins and storms and radiates and slowly consumes its own rings. But we can think about it. And when we do, we are doing something that, as far as we know, nothing else in the Saturn system can do. We are reflecting on our own existence in the context of the cosmos. We are asking why we are here and what it all means, and whether we are alone. These are the questions that Saturn provokes, not because the planet has answers, but because its sheer alienness, its sheer indifference, forces us to confront the questions more honestly than we usually do. In our daily lives, we are surrounded by the familiar, the expected, the comfortable. Saturn strips all of that away. It shows us a world that operates by the same physical laws as ours, but produces results so different, so extreme, so far beyond our everyday experience, that it might as well be from another universe. And it reminds us that our universe is much, much stranger than we typically give it credit for. Let us take one more look at the rings before we go, because there is a particular detail about them that captures something essential about Saturn and about our relationship with it. During Cassini's grand finale, as the spacecraft was making its final orbits between Saturn and the rings, it passed through a region that scientists expected to be hazardous. The gap between the innermost ring and the cloud tops was thought to be filled with particles. Ring material that had drifted inward. Dust. Debris. The mission planners were worried. They turned the spacecraft so that its high-gain antenna, the dish-shaped communication antenna, was facing forward, acting as a shield against potential impacts. And then they held their breath as Cassini dove through the gap at over 70,000 miles per hour. And then something surprising happened. Almost nothing hit the spacecraft. The gap was nearly empty, cleaner than anyone had expected. The instruments detected only a handful of tiny dust particles. The region between Saturn and its rings was a void, a quiet space between the planet and its jewelry. Scientists were puzzled. They had expected more material. The ring rain process should have been filling this region with particles migrating inward. But the data showed otherwise. Subsequent passes confirmed the finding. The gap was surprisingly clean. Whatever mechanism was pulling material from the rings was not depositing much of it in this intermediate zone. It was falling directly into the atmosphere, perhaps along magnetic field lines, bypassing the gap entirely. This small detail, a clean gap where there should have been dust, tells us something important. Even after 13 years of close study, even during the final days of the most sophisticated Saturn mission ever flown, the planet could still surprise us, could still defy our models, could still present a face we did not expect. Saturn will always do this, no matter how many spacecraft we send, no matter how advanced our instruments become. There will always be another surprise, another mystery, another detail that does not fit the current picture. That is not a failure of science. That is the nature of science, and it is the nature of Saturn. The planet is a reminder that the universe is not obligated to be simple. It is not obligated to be comprehensible. It operates according to its own laws, on its own timescales, at its own pressures and temperatures. And sometimes those operations produce things that our minds struggle to accommodate. A hexagonal storm, a rain of diamonds, rings made from the corpse of a moon, an ocean inside a ball of ice the size of Arizona. These things are not designed for our understanding. They simply are. And our job, as curious creatures on a small planet far away, is to look at them as clearly as we can and try, humbly, to figure out what they mean. There is a concept in astronomy called the overview effect. It describes the cognitive shift that astronauts experience when they see Earth from space for the first time. The borders disappear. The conflicts seem petty. The planet looks fragile and precious and alone against the black void. It changes people. It gives them a new perspective. Saturn can produce something similar, even though most of us will never see it with our own eyes from orbit. Just knowing what we know about Saturn, just holding in your mind the image of a gas giant with supersonic winds and hexagonal storms and disappearing rings and hidden oceans, just understanding the scale and the violence and the beauty and the indifference of it all can shift something inside you. It can make you feel smaller, more humble, more grateful, more aware of the extraordinary improbability of your own existence. And that, perhaps, is the most important thing Saturn gives us. Not data, not discoveries, not photographs, although those are magnificent, but perspective. A vantage point from which to look at our own world and see it more clearly. A mirror held up at a distance of nearly 1 billion miles, reflecting back not Saturn's image, but our own. We started this journey with a question. Why is Saturn the scariest planet in our solar system? And we have explored many answers. The winds, the pressure, the storms, the lightning, the crushing interior, the alien moons, the disappearing rings, the sounds, the mysteries. All of these are real. All of them contribute to the sense of unease that Saturn inspires. But the deepest answer, the one that lingers after all the facts have been recounted, is this. Saturn is terrifying because it is real. It is not a thought experiment. It is not a science fiction scenario. It is a physical object, made of physical matter, obeying physical laws, existing right now, at this very moment, in our solar system. The hexagonal storm is raging right now. The winds are howling right now. The helium is raining right now. The rings are dissolving right now. The ocean beneath Enceladus is churning right now. All of it, is happening simultaneously with your life. While you go to work and eat dinner and sleep and wake up and do it all again, Saturn is out there, being Saturn. Enormous, indifferent, ancient, violent, beautiful. And something about it does not make sense. We have spent decades studying it, and we still cannot explain the hexagon fully. We still cannot measure its day precisely. We still do not know how its rings were born. We still do not know whether its moons harbor life. Saturn is full of things that do not make sense. And that is not a flaw in our understanding. That is what makes it the most fascinating, the most terrifying, and the most humbling planet we have ever encountered. If there is one lesson to take from all of this, it is that the universe is not finished teaching us. It has more to show, more to reveal, more to confuse and challenge and awe. Saturn is just one planet around one star in one galaxy among trillions. And it has kept us busy for 400 years. Imagine what else is out there. Imagine what we have not yet seen. Imagine what is waiting for us to build the next telescope, launch the next spacecraft, ask the next question. The story of Saturn is the story of human curiosity, of our refusal to accept that something is unknowable simply because it is far away and hostile and strange, of our insistence on reaching out across millions and billions of miles of cold, empty space, to touch a world we can never inhabit, and listen to a voice we can barely hear. We did that, we are doing that, and we will keep doing that, because that is what we do. We look up, we wonder, and we go. Saturn is waiting. It has been waiting for a very long time, and it is not going anywhere. If this journey through the ring giant resonated with you, consider subscribing to the channel and joining this community of curious minds. We explore the universe together here, one mystery at a time. Leave a comment and let us know which part of Saturn fascinates or terrifies you the most. And if you found value in this, share it with someone who looks up at the sky and wonders what is out there, because the answer is always more than we expected. We will see you in the next one. Until then, keep looking up. But before we go, there is more to say, because Saturn is not a planet you can summarize in a single pass. Every time you think you have reached the end of its strangeness, another corridor opens up. Another door reveals another room full of questions. So let us walk through a few more of those rooms. Let us talk about Saturn's magnetosphere. We touched on the magnetic field earlier, its unusual symmetry, its mysterious alignment with the rotational axis. But the magnetosphere, the region of space controlled by that magnetic field, is a world unto itself. Saturn's magnetosphere is enormous. It extends roughly 1 million kilometers toward the Sun. For perspective, the distance from the Earth to the Moon is about 384,000 kilometers. So Saturn's magnetic influence reaches more than 2.5 times the Earth-Moon distance, just on the sunward side. On the opposite side, the magnetotail stretches even further, blown back by the solar wind into a long, tapering plume that extends millions of kilometers into the outer solar system. Within this magnetosphere, charged particles are trapped. Electrons and ions spiral along the magnetic field lines, bouncing back and forth between the poles, creating radiation belts similar to Earth's Van Allen belts, but on a much larger scale. These particles interact with Saturn's rings, its moons, and its atmosphere, creating a complex electromagnetic environment that Cassini spent 13 years mapping. One of the most surprising discoveries was a radiation belt that nobody expected to find. Cassini detected a previously unknown belt of high-energy particles trapped between Saturn's innermost rings and the planet itself. This belt was shielded from view by the rings, which absorbed most of the particles that tried to cross them. It was an isolated pocket of radiation, cut off from the rest of the magnetosphere, existing in a narrow gap between the rings and the cloud tops. The particles in this belt were likely produced by cosmic rays striking the rings and knocking atoms loose, which then became trapped in the local magnetic field, a radiation belt born from the rings themselves. Another example of Saturn's components interacting in unexpected ways. The magnetosphere also mediates the connection between Saturn and its moons. We talked about the electromagnetic interaction between Saturn and Enceladus, the plasma waves that Cassini detected traveling between the two bodies. But this is not the only such connection. Titan, with its thick atmosphere, also interacts with Saturn's magnetosphere. When Titan is inside the magnetosphere, which it usually is given its orbital distance, the Moon creates a wake in the magnetic field, like a boulder in a stream. Charged particles pile up on one side of Titan and are depleted on the other. The interaction strips ions from Titan's upper atmosphere and carries them along the magnetic field lines, contributing to the plasma environment around Saturn. The moons are not passive objects orbiting a giant planet. They are active participants in a vast electromagnetic ecosystem. They contribute material to the magnetosphere. They absorb radiation. They channel plasma flows. They generate auroras on Saturn's atmosphere, where the magnetic field lines that connect to them meet the polar regions. Each moon leaves a fingerprint on Saturn's magnetic environment. And by reading those fingerprints, scientists can learn about the moons themselves, even from a great distance. Saturn's auroras are another spectacle entirely. Like Earth, Saturn has polar lights, caused by charged particles from the solar wind and the magnetosphere spiraling down along magnetic field lines and colliding with atmospheric gases near the poles. But Saturn's auroras are far more dynamic and far more powerful than Earth's. They can extend thousands of kilometers above the cloud tops, forming shimmering curtains of ultraviolet and infrared light that pulse and shift with changes in the solar wind. Cassini and the Hubble Space Telescope both observed Saturn's auroras extensively. The images show glowing rings of light around the poles, sometimes brightening suddenly in response to solar storms, sometimes dimming and contracting. The auroral emissions on Saturn are primarily in the ultraviolet and infrared, making them invisible to the naked eye. But instruments designed to detect those wavelengths reveal a constantly changing light show, driven by the same fundamental physics that creates our own northern lights, but scaled up to the proportions of a gas giant. And these auroras are directly connected to the eerie radio emissions we discussed earlier. The same magnetic processes that accelerate particles into the atmosphere and create the visible aurora also generate the kilometric radiation that Cassini detected. The radio emissions and the visible aurora are two faces of the same phenomenon, different manifestations of the same underlying physics, and that physics is still not fully understood. The exact mechanism by which the charged particles are accelerated to the energies needed to produce the radio emissions remains a subject of active research. Earth's auroral radio emissions face the same theoretical challenges. Saturn and Earth share this puzzle, connected by the same unsolved problem in plasma physics. Let us now consider Saturn from a different angle, not as a physical object, but as a cultural one, because Saturn has influenced human civilization in ways that go far beyond science. The planet is named after the Roman god of agriculture and time. In Roman mythology, Saturn presided over a golden age of peace and plenty before being overthrown by his son Jupiter. The parallels with the planets are coincidental but poetically fitting. Jupiter, the larger planet, dominates the outer solar system, while Saturn, the elder but smaller sibling, occupies the orbit beyond. Saturday, the day of the week, takes its name from Saturn. In many languages, the connection is preserved, and throughout history, Saturn has been associated with time, discipline, limitations, and the slow grinding of cosmic cycles. In medieval and Renaissance astrology, if you can't sleep, it's not because you're not tired. It's because your mind is still running, replaying the day, looping through the week, landing on something from years ago that has no business keeping you awake. Or you fall asleep fine and wake up at 3 a.m., wide awake, and now you're lying there doing the math on how many hours you have left before the alarm goes off. White noise doesn't fix that. Sleep playlists loop every few minutes and pull you back right when you were drifting. Meditation apps ask you to try, and trying is the problem. Your mind doesn't need to be quieted, it needs somewhere to go. Beyond the Stars is a full collection of long-form narrated space journeys built for a mind that won't stop on its own. Not music, not ambient noise. Calm, steady narration, slow pacing, deep space. Something your mind can follow without thinking. Something continuous enough that the looping just runs out of room. You're drifting through distant star systems, moving past quiet worlds, floating so far from everything that whatever was running in your head gradually loses its grip, without you forcing it. 5 overnight journeys, each one 6 to 8 hours long. No ads, no endings, no sudden sounds at 2 a.m. One purchase, any device, lifetime access. A sleep app costs you every single month, and it still interrupts you. This is $39 once, and it works while you sleep, not while you're trying to. If you're watching this channel, you already know what this kind of content does to a restless mind. Click the link below, get beyond the stars tonight, and actually sleep. Saturn was considered a malefic planet, associated with melancholy, restriction, and hard lessons. Artists depicted it as an old man carrying a scythe, a figure that eventually merged with the personification of time itself. Father Time, with his hourglass and his blade, owes much of his imagery to the planet Saturn. This cultural resonance is not accidental. Saturn's slow movement across the sky, taking nearly 30 years to complete one orbit, made it the most deliberate of the visible planets. It was the most distant planet known to the ancients, the boundary of the known solar system. Beyond Saturn, there was only the realm of the fixed stars. Saturn marked the edge of the world, the frontier, the limit of what was accessible to human observation. When Galileo first observed Saturn through his telescope in 1610, he entered uncharted territory. He saw something no human had ever seen, something he could not understand. His telescope was too crude to resolve the rings clearly, and he described what he saw as a planet with 2 smaller companions, one on each side. 2 years later, when he looked again, the companions had vanished. The rings had turned edge onto Earth, making them invisible through his small telescope. Galileo was baffled. He wrote that Saturn had swallowed his children, an eerie echo of the mythological Saturn who devoured his own offspring to prevent them from overthrowing him. It was not until 1655 that Huygens correctly identified the rings, using a telescope of his own design that was significantly better than Galileo's. And it was not until 1675 that Giovanni Cassini, the astronomer after whom the famous spacecraft and the famous ring gap were both named, discovered the division between the A and B rings, proving that the ring system was not a single solid structure, but a complex collection of orbiting material. From Huygens to Cassini, to Voyager to Cassini again. The 400-year journey of discovery at Saturn has been one of the great adventures of human knowledge. Each generation built on the work of the previous one. Each new instrument revealed something the old ones could not see. And each revelation deepened both our understanding and our sense of wonder. Think about that arc for a moment. In 1610, we could not even tell what the rings were. In 2017, we were flying a spacecraft through them, tasting their particles, measuring their mass, and using them as seismographs to study the interior of the planet. In just over 400 years, we went from total confusion to intimate knowledge, from squinting through crude glass lenses to deploying billion-dollar robotic explorers. That is the trajectory of human curiosity. That is what happens when you refuse to stop looking, and we are still on that trajectory. The next generation of telescopes and spacecraft will take us further. They will answer some of the questions we have today and generate entirely new ones we have not yet thought to ask. That is the pattern. That has always been the pattern. Saturn does not run out of mysteries. It only reveals them in layers at the pace of our ability to observe. Let us spend a few more moments with the moons, because there is one more story worth telling about the relationship between Saturn, its moons, and its rings. The rings and the moons are not separate systems. They are connected, deeply and physically connected. The moons create the rings create the moons. Material flows between them constantly, driven by gravity and collisions and electromagnetic forces. We talked about how the rings might have been formed by the destruction of a moon, but the reverse process also happens. Within the rings, material can clump together under its own gravity, forming small moonlets that grow by accreting surrounding ring particles. These moonlets are called propeller moons because of the characteristic propeller-shaped disturbances they create in the ring material around them. Cassini discovered dozens of these propeller features in the A ring, each one marking the location of an unseen moonlet embedded in the ring, slowly growing or slowly being eroded by collisions. Some of Saturn's known small moons may have formed this way. Pan and Daphnis, the tiny moons that orbit within gaps in the A ring, are thought to be accretions of ring material that gathered around a dense core. They are, in a sense, children of the rings, born from the debris of an ancient catastrophe, shaped by the same gravitational forces that sculpt the rings themselves. And the process is not static. It is ongoing. Right now, inside Saturn's rings, moonlets are forming and breaking apart. Material is being exchanged. Particles are colliding, sticking together, splitting apart, migrating inward, spiraling outward. The ring system is alive, not in the biological sense, but in the dynamical sense. It is a system in constant motion, constantly evolving, constantly changing. The rings you see today are not the same rings that existed 1,000 years ago. The particles have shifted. The structures have changed. The moonlets have grown or shattered. It is a snapshot of a process that never holds still. This dynamism is what makes Saturn's rings such a valuable natural laboratory. They allow us to study the physics of disk accretion, the process by which small particles come together under gravity to form larger bodies. This is the same process that built the planets. 4.5 billion years ago, the solar system was a disk of gas and dust orbiting a young star. Within that disk, particles collided and stuck together, forming pebbles, then boulders, then planetesimals, then planets. The same physics, the same gravity, the same collisional dynamics. Saturn's rings are a living example of that ancient process, happening in real time, right next door. By studying the rings, we can test our theories of planet formation. We can observe how density waves propagate through a disk of particles. We can watch how moonlets open gaps and create wakes. We can measure how collisions redistribute material. Every observation of Saturn's rings is also an observation about the origin of worlds, including our own. There is also the question of what the rings look like from Saturn itself. We have never seen this view, and barring some extraordinary future mission, we probably never will, but we can imagine it. From the cloud tops of Saturn, looking upward, the rings would arc across the sky from horizon to horizon, a vast, luminous band, bright and sharp at the inner edge, fading to translucency at the outer edge. Depending on your latitude, you would see the rings at different angles. From the equator, they would appear edge-on, a thin, bright line cutting the sky in half. From higher latitudes, they would spread into a broad arch, casting shadows on the cloud deck below during certain seasons. At night, if Saturn's cloud tops could be considered to have a night side, the rings would reflect sunlight back down onto the planet, illuminating the atmosphere with a soft, diffuse glow. Ring shine, a gentle light from above, cast by billions of ice particles orbiting overhead. It would be one of the most spectacular sights in the solar system, and no eye has ever seen it. The universe is full of views that no one has ever seen. Sunsets on planets orbiting binary stars, the glow of nebulae seen from within, the surface of a neutron star, the horizon of a black hole. Saturn's rings from below are just one entry on that infinite list, but they remind us that beauty exists whether or not anyone is there to witness it. The universe does not perform for an audience. It simply is. And perhaps that is the final lesson Saturn offers. The universe does not owe us comprehension. It does not owe us beauty. It does not owe us meaning. These are things we bring to it ourselves. We look at Saturn and we see terror and beauty and mystery and scale. But Saturn does not see anything. It does not know it is terrifying. It does not know it is beautiful. It does not know its rings are disappearing, or that its moons might harbor life, or that its hexagonal storm has puzzled a species of primates living on a rock nearly 1 billion miles away. Saturn simply exists. In all its enormity, in all its strangeness, in all its violent, golden, ring-wrapped, storm-scoured, diamond-raining, helium-weeping, magnetically perfect, rotationally mysterious, cosmically ancient glory. And we are the ones who decided to pay attention. That decision, the decision to look up and wonder and investigate and explore, is the most human thing about us. It is what separates us from every other known life form in the universe. Not our intelligence, necessarily, not our technology, but our curiosity, our unwillingness to accept ignorance, our compulsion to send machines across billions of miles of vacuum to photograph a storm on a planet we will never visit. Saturn does not care that we did this, but we should, because it says something about who we are, about what we value, about the kind of species we choose to be. We are the ones who looked at a golden dot in the sky and thought, I want to know what that is. And then we spent 4 centuries finding out. And we are not done yet. The scariest planet in our solar system is also the most instructive. It teaches us about gravity and chemistry and time and scale. It teaches us about the fragility of beauty and the persistence of mystery. It teaches us that the universe is under no obligation to be comforting, but that there is comfort to be found in the act of understanding, even when the understanding is incomplete. Something about Saturn does not make sense, and that is exactly why we keep looking. If this journey through the ringed giant resonated with you, consider subscribing to the channel and joining our community of curious minds. We explore the vast mysteries of the cosmos together here, one wonder at a time. Drop a comment below and share which part of Saturn's story fascinated or unsettled you the most. And if you found value in this, pass it along to someone who stares at the night sky and wonders what secrets it holds. The answer, as always, is more than any of us expected. We will see you in the next one. Until then, keep looking up and sleep well. Actually, before we truly wrap up, there are a few more things I want to share with you, because Saturn's story has corners we have not yet explored. Small details that, when you piece them together, reveal something larger. Let us talk about the Cassini division, the famous gap between the A ring and the B ring, first spotted by Giovanni Cassini in 1675. From Earth, it looks like an empty space, a dark band separating two bright rings. For centuries, astronomers assumed it was simply a gap, an empty zone where no ring particles existed. But Cassini the spacecraft showed us that this was wrong. The Cassini division is not empty. It contains ring material, thin, faint, but present. The particles there are darker and sparser than in the main rings, but they exist. The division is not a void. It is a region of reduced density, maintained by the gravitational resonance with the moon Mimas. This distinction matters because it changes how we think about structure in the rings. The rings are not a series of discrete bands separated by empty gaps. They are a continuous disk with variations in density, sculpted by an intricate web of gravitational forces. Some regions are dense and bright. Others are sparse and dark. But there is material everywhere. The ring system is a spectrum, not a collection of separate objects. And the apparent gaps are just low points in that spectrum, not true absences. This subtlety extends to the entire ring system. When Cassini observed the rings at high resolution during its close approaches, it found structure at every scale it could resolve. Ringlets within ringlets, waves within waves, clumps that formed and dissolved on timescales of hours. The rings are fractal in their complexity. No matter how closely you look, there is always more detail to be found. This is one of the reasons that studying Saturn's rings has been so rewarding and so challenging. There is no bottom to the detail, no resolution at which the rings become simple. And then there are the ring particles themselves. We said they are mostly water ice, and they are. But Cassini's instruments revealed that the composition is not uniform. Some particles are coated with a thin layer of darker material, possibly silicates or organic compounds. Others are almost pure ice. The proportion of contaminants varies from ring to ring, and even within a single ring. The inner C ring, for example, has a higher proportion of silicate material than the outer A ring. This gradient in composition is another clue to the ring's history and another piece of evidence in the debate over their age. During the grand finale, when Cassini dove between the planet and the rings, its cosmic dust analyzer captured and analyzed 163 individual dust grains from beyond the Saturn system, cosmic dust that had drifted in from the interstellar medium and the Kuiper belt. By measuring the rate at which this external dust was being added to the rings, scientists could estimate how quickly the rings should be darkening, and the answer supported the young ring hypothesis. The influx was high enough that if the rings were billions of years old, they should be much dirtier than they are. The fact that they remain so bright and so pure means they have not been exposed to this cosmic rain for very long. 163 grains of dust. That is all it took to help settle one of the longest-running debates in planetary science. 163 microscopic particles, each one weighed and measured and analyzed by an instrument flying at tens of thousands of miles per hour through the gap between a planet and its rings. The precision of this measurement is extraordinary, and it is a testament to the ingenuity of the engineers and scientists who designed Cassini's instruments and planned its final orbits. Let us also revisit Enceladus for a moment, because there is one more detail about this remarkable moon that deserves emphasis. When Cassini flew through Enceladus's plumes and detected molecular hydrogen, it was a pivotal moment. Molecular hydrogen in the plume material is significant because on Earth, it is produced by hydrothermal reactions between hot rock and water, specifically a process called serpentinization, in which certain iron and magnesium-rich minerals react with water at high temperatures to produce serpentine minerals and hydrogen gas. This process is common at Earth's mid-ocean ridges, where seawater infiltrates cracks in the volcanic rock and is superheated by magma below. The detection of molecular hydrogen in Enceladus's plumes suggests that the same process is happening at the bottom of the moon's ocean. Hot rock is reacting with liquid water, producing hydrogen gas that rises through the ocean and is expelled through the tiger stripe fractures in the south polar ice. This means there is a chemical energy source at the bottom of the ocean, an energy gradient, a disequilibrium. And on Earth, every known ecosystem ultimately depends on some form of energy gradient to sustain life. At hydrothermal vents on Earth's ocean floor, microorganisms called chemotrophs use the chemical energy from hydrogen and other compounds to power their metabolism, completely independent of sunlight. They thrive in total darkness, at crushing pressures, at temperatures that would kill most other life forms. If similar organisms exist at the bottom of Enceladus's ocean, they would represent a second independent origin of life in our solar system, and that would change everything. It would mean that life is not a fluke. It is not a one-time event that happened on Earth through some improbable sequence of coincidences. It would mean that life is a natural consequence of the right chemistry in the right conditions. And since those conditions appear to exist in multiple places in our solar system alone, the implication is that life might be common throughout the universe. We do not know if there is life on Enceladus. We have no evidence of biology there. Only the evidence of conditions that, on Earth, are associated with life. But the possibility is real enough that it drives the design of future missions. It motivates the development of new instruments. It shapes the priorities of space agencies around the world. Enceladus is not just a moon. It is a question. A door that might open onto the most profound discovery in the history of science. And Saturn is holding that door. There is also the matter of tidal forces. We mentioned the Roche limit, the distance at which a body will be torn apart by tidal forces. But the tidal interactions between Saturn and its moons go far beyond simple destruction. Tidal forces are responsible for the geological activity on Enceladus. As Enceladus orbits Saturn, the planet's gravity pulls on it unevenly, flexing and deforming the moon's interior. This flexing generates heat, in the same way that repeatedly bending a paperclip makes it warm. The amount of heat generated depends on the moon's orbital eccentricity, how much its orbit deviates from a perfect circle, and on the internal structure of the moon. Enceladus's orbit is slightly eccentric, kept that way by a gravitational resonance with the larger moon Dione. This resonance prevents Enceladus's orbit from circularizing, ensuring a continuous supply of tidal energy. Without this tidal heating, Enceladus's ocean would freeze solid. The moon is too small and too far from the sun to maintain liquid water on its own. Saturn's gravity is what keeps the ocean liquid. It is Saturn that powers the hydrothermal vents at the bottom. It is Saturn that drives the geysers at the South Pole. It is Saturn that maintains the conditions that might, just possibly, support life. There is a profound irony here. Saturn, the terrifying gas giant, the planet of crushing pressure and howling winds and diamond rain, is also potentially responsible for nurturing the most delicate and precious thing we know of: life. The same gravitational force that tears moons apart and devours ring particles is also the force that warms an underground ocean and powers the chemistry of potential biology. Creation and destruction, driven by the same mechanism. This is the duality at the heart of Saturn's character. This is what makes it so compelling and so difficult to categorize. It is not simply a destroyer. It is not simply a creator. It is both, simultaneously, without contradiction, because the universe does not deal in neat categories. It deals in physics, and physics does not choose sides. Saturn's influence on its moons extends even further. The orbital dynamics of the satellite system are a web of resonances and interactions. Mimas and Tethys are in a 2-to-1 resonance, meaning Mimas orbits Saturn exactly twice for every one orbit of Tethys. Enceladus and Dione are in a similar 2-to-1 resonance. These resonances lock the moons into synchronized orbits, preventing their paths from evolving independently. They also pump energy into the moon's orbits, maintaining their eccentricities and driving the tidal heating that keeps some of them geologically active. This interconnectedness means that changes in one moon's orbit can ripple through the entire system. If a large impact were to alter the orbit of one moon, the resonances would transmit that perturbation to the others, potentially destabilizing the system. The Saturn satellite system is a finely tuned machine, each part connected to the others through the invisible threads of gravity. It has been running for billions of years, but it is not eternal. Over geological time, the orbits will evolve. Resonances will be broken. New ones will form. Moons will migrate. And the system will slowly, inevitably change. Nothing in the Saturn system is permanent. Not the rings, not the moon's orbits, not even the hexagonal storm, though it has outlasted every other atmospheric feature we know of. Everything is temporary on a cosmic timescale. Everything is in motion. Everything is evolving. And that, really, is the heart of Saturn's message to us. Change is the only constant. Even in a system as massive and as seemingly stable as Saturn's, the forces of gravity and time are always at work, always reshaping, always eroding, always building something new from the remains of something old. The rings were born from destruction and will end in dissolution. The moons were captured or accreted and will one day be scattered or consumed. The storms arise and subside. The hexagon persists but may not persist forever. Even Saturn itself is slowly cooling, slowly contracting, slowly evolving toward a future state that we cannot predict. We are witnessing one moment in an ongoing story, a story that began 4.5 billion years ago and will continue for billions more. We see Saturn as it is now, in this particular configuration, with these particular rings, these particular moons, these particular storms. But Saturn has worn many faces over its long existence, and it will wear many more after we are gone. The privilege of being alive at this moment is that we get to see this particular version of Saturn, this particular arrangement of ice and gas and gravity. And through the instruments we have built and the missions we have flown, We have been able to capture more detail about this particular moment than any generation before us. That is not something to take for granted. It is something to celebrate. And with that, we truly have reached the end of our journey through the ringed world. Saturn, the golden giant, the scariest planet in our solar system, the most beautiful, the most mysterious, the most instructive, and the most humbling. Something about it does not make sense. And maybe that is the point. If you made it this far, thank you. Thank you for your curiosity. Thank you for your attention. And thank you for sharing this time with us as we wandered through one of the most extraordinary places the universe has to offer. Subscribe if you have not already. Join this community of explorers. And leave us a comment. Tell us what you think. Tell us what you want to explore next. Because the cosmos is vast, and we have barely scratched the surface. Until next time, keep wondering, keep questioning, keep looking up, and sleep well tonight, knowing that 1 billion miles away, Saturn is still spinning, still storming, still raining diamonds into the dark. Good night.